Hey guys, welcome to Pre-Calc, lesson 8A.7, changing units of time and modeling. Let's start with a warm-up here. If you invest $15,000 at an interest rate of 6.6% compounded monthly, what is the value after 8 years? Hopefully at this point, this question is pretty straightforward. $15,000 times 1 plus the interest rate, so that'd be 0.066, divided by the number of times it's compounded. So if that's monthly, obviously n is 12. To the 12 times number of years, that'd be 8. All right, and throwing that into the calculator, I got $25,396.30. Part B, what is the annual rate of return to the nearest thousandth percent? So notice in the last lesson we talked about, if it just says annual rate of return, you just give the common ratio. But if it goes ahead and then says to a percent or a decimal of a percent, then you would round that to the nearest hundredth. So in this case, annual rate of return, we need the B value, which is this term right here. Here's your A, this is your B, and that's your X, the T, the time. So all I really need to calculate here would be this 1 plus 0.066 over 12 to the 12th, and that's 1.06803. So most of you can probably convert this in your head by now, but basically what we do to get the percent increase or decrease is we take that number and we subtract 1 from it. So that gives us our 0.06803. To get that to a percent, we move this over 2 places and then round to whatever it says, hundredth. So that's 2 places right there, 6.80% increase or rate of return. Okay, next, car depreciates 12.25% per year. Write 2 exponential functions that model the maximum and minimum depreciation. So back on day 4, we talked about maximum and minimum. And one of those was PERT. So that's this model right here, right on the right side. It's just the way my notes are. And the other model was simple interest. So it's something like this. Our principal 1 plus, or in this case 1 minus r to the t. Okay, well, let's do both of these. I'll stick with the one on the left here. A equals. P is just our principal. We don't know what it is, so it'll just stay P. 1 minus 12.25% is 0.1225 to the t. And that is simply 0.8775 to the t. Using our PERT model, it would be A equals P, which we don't know, E. Now, when we deal with PERT and we depreciate, we make that exponent negative. So it would be negative 0.1225 to the t. And that's good enough right there. We could take that. What's interesting, though, I don't know if I still have it on my calculator, this is the minimum depreciation. You would think, well, wait a minute, it's maximum appreciation. It ends up being the minimum depreciation. And this one over here is the maximum depreciation. And if you don't believe me, throw this into your calculator right here, and you're going to get a decimal that's more than this, which means more remains each year or less leaves. Okay, moving on. Today's lesson, changing units of time in exponential functions. Pretty important concept here. When changing to a larger unit of time, multiply the exponent by the conversion factor, which obviously just depends on what we're converting to. You know, days to hours, it's 24 to 1, that sort of deal. When changing to a smaller unit of time, divide the exponent by the conversion factor. So we're going to practice a bunch of these, and hopefully by the end we'll have the hang of it. All right, a company's revenue increased by 5.7% over the previous year. If this continues, find an expression that can be used to determine each. The annual percent increase. Well, we have to take a look at this problem here to see what unit of time that is. 5.7 over the previous year. So that is annual. So nothing's going to change for this example. This is the most basic one we'll have. A equals P times 1.057 to the T. So I sort of did that quickly. I was using this model, 1 plus R to the T, and it increased by 5.7, so that's 0.057. Okay, so that's pretty straightforward. But now it says the monthly percent increase. Now remember, these are exponential functions. They're not linear. All right, so I can't just divide the interest rate by 12. It doesn't work that way. So what we do have to divide is the exponent. So this is what I get for the year. For the month, it can't be this. It's got to be less than this. But what do we have to do to the exponent to make this less? We have to divide. All right, so we're going to change our unit of time to m months, and we're going to take this and just divide that by 12. Okay, so now I've got A equals P times 1.057 to the m over 12. Or if we take that 1 over 12 and move it in, A equals P times 1.00463 to the m. Now hopefully this makes sense to you guys, because think about it. 5.7% is for the whole year, so that kind of makes sense. This is a year. But if this is now a month, this has to be a smaller number, because otherwise I'd be getting way more interest than what this states here. So that's why when we bring that exponent inside, it should make sense that you divided that exponent. Okay, decade percent increase. So what am I going to get for a whole decade? Well, that'll be my 1.057 times 10d. Because a decade is bigger than a year, if you're going to a larger unit of time, you need to multiply that exponent. Or A equals P times, let's see, what do I get there? 1.74080 to the D. And lastly here, quarterly percent increase in terms of Q quarters. Well, I'll take my original, which is 1.057. And since the original was a year, now I'm going into quarters. I have to divide that original one by 4. And I'm just changing the variable to represent quarters. And if you bring that inside, you end up getting 1.01396 to the Q. So let's check this out. I've already done this. Normally, if it just says write an expression, you're fine leaving it like this. But I know the next example, we have to find the percent increase and decrease per unit of time. So states the nearest hundredth of a percent, each percent increase from above. The annual percent increase, well, that's pretty simple. That's 5.70 if you want to round to 100%. Where'd that come from? It came from this right here. Right? Subtract 1 from it, move it over 2 places. That's what we had. That's what it is per year. Monthly percent increase. Here's where it's critical that you understand. You don't just take this and divide it by 12. It doesn't work that way. You have to go through this process and then take a look at what we have here. So if we move this over 2 places, all right, it looks like it's 0.46. So the monthly percent increase is 0.46% to nearest hundredth. Decade percent increase. Well, I'm not going to take this and multiply it by 10 because it's exponential. I'm going to take my decade exponential function, take a look at this, subtract 1 from it, move that over 2 places, 74.08%. And this is a great illustration. Notice that times 10 is 57%. But over the decade, I get 74%. Why is that? because it's 5.7% a year. It's not 5.7% for the decade. So think about how this works. There's your exponential model. So after 1 year, if you're at 5.7%, it becomes a lot more. It's not linear. Quarterly percent increase, I'm going to take this one right here, subtract 1, move that over, 1.40 looks like. Oops, wrong color, sorry. 1.40% increase. Okay, let's try a couple more. If the population was growing at a constant rate of 15% every 6 years, write an expression in terms of the yearly percent increase. So you can pick whatever variable you want. For yearly, I'll use just a t. But let's think about how this works. Yearly population. So I don't know what the initial amount is. I'll just leave it p. Times 1.15. I'll take 1 plus 15%. If t represents a year, I have to divide it by 6 because this increase inside here is over 6 years. So I'm changing a unit of time from 6 years to 1 year. And now let's bring that in. Okay, so or A equals P times, I got 1.02357 to the t. Now, like I said, if you just have to write an expression, this is fine. Yeah, that's what it is for 1 year. But I know I have to state the annual percent increase, so I'm going to need this term anyway. So that's why I did it like that also. Annual percent increase. You're going to take this, subtract 1 from it. Okay, so 1.02357 minus 1 is obviously 0.02357. Convert that to a percent, move this over 2 places, and round to nearest tenth. 2.4% increase. That's what it is every year, annual. Okay, next one. Investments monthly increase is 0.25% from the previous month. If this continues, find an equation that can be used to determine each. The monthly percent increase. So when these units of time are the same, month and month, it's just that simple, y equals ab to the t, and this b term is 1 plus r, 1 minus r if it's a depreciation. So for this one, I'll do a equals our initial amount, which we don't know what it is. It's going to change. 0.25%. We have to be careful. That's 0.0025. So that's 1.0025 to the m months. Now, annual. How does this unit of time compare to m months? It's more. More means multiply. So what I'll do now is I'll take this function that I have up above, I'll take my variable and I'll multiply it by 12. And they just want you to change the name of the variable to t in this case. All right, or let's bring the 12 inside. That is a equals principal times 1.03042 to the t. The last part of this example, what would be the percent increase to nearest tenth after 8 years? Well, you have two approaches. One of them is you could take this monthly increase, take that, multiply it by 12 to get to years, then multiply that by 8. This is the method I'm going to use. Or since you've established what it is per year, you could take this one here, multiply that by 8, which just brings that inside. I'm going to avoid that one just because I had to round to get this, I had to calculate, so I'll just take this one up here. And so that's A equals P, it's 1.0025, and then times 12 to convert it to years, times 8 for 8 years, and then I have my, I don't know, whatever variable you want to keep up there. So basically you need to calculate this. All right, let's keep it going here. That's P. That gives me 1.27087, and that'd be to the x. So remember, our x here represents 8 years. Percent increase, take this, subtract 1, so that will be 0.27087 0.087. Move this over 2 places, and that will be 27.1% increase over 8 years. All right, well, let's move on. All right, nobelium decays exponentially with a half-life of 23 seconds. Write an equation which represents the amount remaining of 100 milligrams of nobelium after S seconds. All right, so that's just our standard half-life model. A equals 100. This is going to be 1/2. And remember, it's T over K, but this time your T is in seconds. So S seconds, this would be an S, and then the half-life is 23. Now it looks like it's 5 over 23, but this is an S right here. I apologize for that. Now, let's say you didn't know your half-life formula. You could derive it. You could do it this way. I know this general formula, y equals AB to the t. And we have a data point here. It says it decays exponentially with a half-life of 23 seconds. So you could just make up some numbers. You could call it 1/2. Let's assume, we're starting with 100, so perfect. 50 equals 100 times b to the 23. Because after 23 seconds, half of it's remaining. And then check this out. So we'll divide by 100, so that gives us our 0.5 equals b to the 23. And then to undo that exponent, take both sides to the 1 over 23 power. So your b term ends up being 0.9703. So here's another expression that's equivalent to the 1 over on the left. A equals 100 times 0.9703 to the s. These two are equivalent. This is a lot easier, obviously, if you know your half-life formula, but if you don't, this is a modeling situation, which is what we're going to get into next. All right, write an equation which represents the amount remaining of 100 milligrams of nobelium after m minutes. So basically what we're doing now is we're going from seconds to minutes. A larger unit of time means you're going to multiply this exponent by 60. So if I want to use this model here, I just need to multiply this by 60. So let me write that one down. A equals 100 times 1/2 or 0.5 to the 60m over 23. If you're using this model on the right, you would have to multiply this by 60. Okay, so that would be A equals 100 times 0.9703 to the 60m. And we're just changing the name of that variable. So either one of those would be fine. All right, so on this page here, it's just a collection of all of the formulas that we use in the unit, compound interest, and this only deals with money. When we're talking about like elements or bacteria, we never use compounded. This only deals with financial world. Then we have our continuous growth. We have our half-life formula here. We have simple appreciation and depreciation. And then this is our PERT, continuous appreciation, depreciation. So our next task is to find an equation given some data points. So this here says find the exponential growth model in the form y equals, you know what? I have to change this. We do not know how to do, theoretically you know how to do natural logs. We haven't covered it yet in this course. So after our next unit, you'll be able to do this application. Let's change this to y equals ab to the x. Okay? So I want it in this form. All right. Given the ordered pairs 0, 2, and 326, one of the things that we'll do to make it a little bit easier on you is we'll always give you the value of a. Remember, this is your y-intercept, so I know a is 2. And I'll give you another point, which gives you an x and a y. So what we're going to do is we'll plug this in for a, that in for x, that in for y. Here, here, and there. And solve for b. All right, so y is 26 equals a, which is 2, times b to the x, which is 3. Divide both sides by 2, you get 13 equals b cubed. And then we'll just take the cube root or the 1/3 power of both sides, whatever's easiest for you guys. And I got b to be 2.35133. So my model is going to be y equals a, which is 2, times that b value, 2.35135 to the x. Use this model to find y when x is 10. So we're just going to plug in a 10 there. Y equals 2 times this to the 10th. And I got 10,331.8. And it says, what is the percent change to nearest hundredth per x units of time? So we're going to take this number here, subtract 1. All right, so let's do that. 2.35135 minus 1 equals 1.35135. Move this over 2 places. So that's going to be 135.4% increase. All right, let's move on. Example 6. All right, more modeling. According to a recent survey, the population of Houston, Texas, and Detroit, Michigan are, so it gives you the populations in 1990 and in 2000. So in 1990, we're going to make this t equals 0, and then 2000 we'll make that t equals 10. And you've got a couple options, but because we haven't done natural logs yet, I'm going to use this model for both. A equals AB to the t, or population equals AB to the t, or however you want to think of it. Okay, so it says find the exponential model of growth for Houston and Detroit. So I'll do Houston over here and Detroit over there. So remember, this gives you your A value. That's at time t equals 0. So for Houston, my data points then would be when x is 10, y is this. And then for Detroit, when x is 10, y is that. So I'll be plugging into this model. There's your y, if you will. We know what A is for both. And then we'll be plugging in 10 for t. All right, so for Houston, I got 2.65 equals 2.3 times b to the 10th. Divide by 2.3. It's just some calculator work. 1.1522 equals b to the 10th. And then remember, to undo that, you take both sides to the 1 over 10 power, or you can take it to the 10th root. It doesn't matter. And I got 1.01427. So here's my model. I'll use y equals 2.3 times 1.01427 to the t. So that's the population model for Houston. Now for Detroit, just same process, different numbers. 2.74 equals 3 b to the 10th. Divide by 3, I got 0.9133 repeating. So let me throw a couple more in there. Equals b to the 10th. Take both sides to the 1 over 10 power. And here b is 0.990976. So this model is y equals 3 times 0.990976 to the t. So obviously here, I mean, you can tell from the chart, but we've got Houston that's growing because their b value is greater than 1. And then we've got Detroit, which is shrinking because its b value is less than 1. All right, predict Houston and Detroit's population in 2020. So in 2020, remember, t equals 0 is 90. So in 2020, t equals 30. So I'm just going to plug into the models I got up above. So again, here's Houston. Y equals 2.3 times 1.01427 to the 30th. And I got 3.518. Now remember, that's million. And then for Detroit, I got y equals 3 times 0.990976 to the 30th. And for that, I got 2.286 million. Find the annual percent increase, decrease for Detroit and Houston. Okay, so I'm going to use this model. You can see them here. I'll use that value and that value. So for Houston, we're increasing. So I'm going to take that B value, 1.01427, and subtract 1. So 0.01427. And then it doesn't say what to round to. Let's just go nearest 10th. Well, actually, let's go nearest 100th. That's what I did in my notes. And then just move that over 2 places. So it's 1.43% increase. And then for Detroit, since it's less than 1, I have to take 1 minus 0.990976. And I got 0.009024. Move it over 2 places. So that's 0.902% decrease. I went to nearest thousandth there. Okay, so one more example. And this one's kind of interesting, a little bit different than what we've seen before. They're going to give you an exponential function. This one represents advertising costs. So it says, after discontinuing all advertising for a certain product in 1994, the manufacturer noticed a decrease in sales according to this model, which doesn't look anything like what we've done yet in this unit. S is the number of units sold. T equals 0 represents 1994. In 1996, the company sold 300,000 units. So that's a data point. Okay, so here we know when T equals 2, big S equals 300,000. A, how many units were sold in 1994? Well, I don't really understand how this works, right? It doesn't look like our typical exponential model. So I don't know what the initial value is. And it didn't tell me what the population was in 1994, how many units sold, in 1994. But if we think about 1994 and what T equals 0. And look at T up here. It's an exponent. Well, I don't care what K is. K times 0 is 0. So this exponent becomes a 0. And remember we said anything to the 0 power is just 1. So this goes away. When T equals 0, I can calculate what the sales were. 500,000 divided by 1 plus 0.6. And you can put it times 1 in there, but basically what happens is this goes away. So let's throw that into the calculator, and we get 312,500 units. Find the exponential model by finding K. All right, so this isn't real easy, but remember we've got this data point here. So I know S is going to be 300,000. That's going to go there. T equals 2. That's going to go there. All right, so let's work that out. So 300,000 equals 500,000 divided by 1 plus 0.6 e to the 2k. So the algebra here is pretty impressive. What we're going to do, if you think about this proportion, that's just going to save a little bit of time, you can interchange the means and extremes. So think of this as being over 1. I'm going to swap these two out. So the 1 plus 0.6 e to the 2k will go up here, and the 300,000 will go down there. Okay, so 1 plus 0.6 e to the 2k equals 500,000 over 300,000, or 5/3. So all of a sudden, just by doing that, this became a lot easier. Now we'll subtract 1. 0.6 e to the 2k equals 5/3 minus 1 is just 2/3. Now multiply by 0.6. All right, so that gives me e to the 2k equals, I kept it as a fraction, 10/9. And unfortunately, there's no other way to solve this other than to use natural logs. So this is just a little preview of what you can expect next unit. To solve for an exponent, we have to take the natural log of both sides. And if you remember, then that comes out front. So I've got 2k times natural log of e equals natural log of 10/9. And the beauty of this is the natural log of e is just 1. Now I just divide both sides by 2. and K equals 0.05268. So my model, I have to write the whole model out, S equals 500,000 divided by 1 plus 0.6 e to the 0.05268 times t. Wow, that's a lot of work. Upper level question right there for sure. And then lastly, predict what the sales will be in 2020. So we had to figure out what t is. You just subtract 94, so that's going to be 26. And plug into this fun function we just found. So S equals 500,000 divided by 1 plus 0.6 e to the 0.05268 times 26. Just take your time, put that into the calculator, create that fraction. I get 148,789 units. Remember, no decimal here as you're talking about whole units. Whew, that was a long lesson, guys. I appreciate you sticking with me. As usual, reach out if you have any questions whatsoever. As you head towards the unit exam here, we've got a review and a work session left. So let us know if you have any questions, okay? Thanks for watching, and we'll see you in class soon.